Hi, I'm sorry that I can't be here today, but I just wanted to make sure that we didn't have any gaps in your education. Unfortunately, I had to go to the doctor with Amaya. But Mr. Hoy is going to be here to help you out as we travel through the world of water potential. So let's first start off with where we left off, and that was the structure of the cell membrane. And if you take a look here, you'll see the phospholipid bilayer, and you'll see that there is a transmembrane protein. If you remember correctly, any protein that enters into the phospholipid bilayer is called an integral protein, and a transmembrane protein is just an extra descriptor for a protein that extends through both sides of the phospholipid bilayer. In the phospholipid bilayer, there are proteins embedded, and those proteins do a host of different jobs. We have transport proteins, which help move ions and other food particles, etc., from one side of the cell membrane to the other. We have some proteins that are associated with enzymatic activity, and as you know, enzymes make chemistry happen, so they'll be doing chemical reactions. Then we also have proteins that are used for reading signals from outside of the cell and communicating those signals into the inside of the cell. We'll be talking a lot about those later. We have certain proteins that are helpful for your immune system. They assist in cell-to-cell recognition, and those proteins allow your immune system to know that that particular cell is supposed to be there. Then we have proteins in the cell membrane that help two cells stick together. So for tissues, when you need the cells to stay in place, they'll actually have these proteins fused together so that your cells don't move about, which is nice. And then we have special proteins that are associated with the cytoskeleton in the extracellular matrix, and really their job is to help kind of feel out what's going on outside the cell and help funnel communication and signaling molecules towards the signal recepting proteins. All right, so those are the 6 major jobs that the proteins have in the cell membrane. And the cell membrane is a very complicated structure. As we know, it's a fluid mosaic model, but how is it produced? You should know by now that the smooth endoplasmic reticulum is responsible for making carbohydrates and for making other lipid type molecules for the cell to secrete, but also it helps to generate additional cell membrane. So as the smooth endoplasmic reticulum is generating the phospholipid bilayer, it bubbles into the rough endoplasmic reticulum. The rough endoplasmic reticulum oftentimes will fill those bubbles with proteins, and sometimes those proteins will actually be embedded into the cell membrane at that time. In some circumstances, the protein is not embedded into the cell membrane until it reaches the Golgi apparatus. So we've got molecules coming from the smooth endoplasmic reticulum and the rough endoplasmic reticulum, and you can see here that this is a protein extending through the phospholipid bilayer, and it's going to go into the cis side of the Golgi apparatus. We've already discussed this. Cis is same side, so the same side as the nucleus. So these vesicles are going to bubble into the Golgi apparatus, which is going to manipulate and help repackage those proteins. You can see now that this glycoprotein has been altered, and it now is slightly different in structure from the original protein that it had. And then it's going to slowly move towards the membrane, and you can see that this is the outside. This is going to end up being the inside of the cell membrane once it joins. So let's take a look at what happens here. As this double layer gets added into the outside of the cell membrane, you can see that this side, which was on the outside, is now stuck on the inside. And this side that's on the inside is now exposed to the outside surface of the cell. Do you guys see that? I hope so. So the cell membrane's major function is to protect the cell and to let certain things in and certain things out. And we call that semi-permeability because it's selective as to what it allows in and out. Now there are certain molecules that the cell membrane allows to move pretty freely across the surface. We talked about how small nonpolar molecules can move through the phospholipid bilayer pretty easily. But then we also talked about water. We know that water's polar, so how is it that water moves so easily through the cell membrane? Well, there's special transport proteins called aquaporins that allow the free movement of water, and they're actually specially constructed so that the water can move so freely. And we've talked a little bit about tonicity and what tonicity means. So tonicity refers to the amount of dissolved sugars and salts in a fluid. And the tonicity, as more sugars and salts are dissolved into a fluid, you'll see more dots are in that side. So those dots are actually representing, in this case, molecules of dye, but in most cases they be representing salts and sugars. And here's the membrane. Oh, I've lost my pointer. Give me a second. Oh, man. Let's see if it can find me again. Okay, there we go. There's our cell membrane, and you can see that there's a random movement of these particles, and then some of them are going to go from high concentration to low concentration. So the net diffusion is going to go across until there's an equilibrium. Once there's an equilibrium, the particles will move back and forth, but there won't be a net change in concentration. So you can see here that there's no net change in concentration, that the particles are moving back and forth, but they're both in equilibrium. So what happens in this type of situation? In this type of situation, where you've got a semi-permeable membrane that allows the movement of water but does not allow the movement of these particles, you're still going to have the water molecules go from high concentration to a lower concentration. Now, what makes this a lower concentration? Because you have so many dissolved salts, then the water is going to move towards that to try to make it a state of equilibrium on both sides. So if you were to leave the situation alone for a while, it would end up where the water actually moves around over here until this is in equilibrium. So you'd actually have the movement of the water down until you have the same concentration on sugars on both sides of the membrane. So this leads to the concept of water potential. Some things that I want you to take home from this will be the fact that water potential moves from a high concentration or high water potential to a low water potential. I would like you to know that the water potential of DI water is 1. Solute water potentials are always equal to or less than the total water potential for a system. And I want you to know that, I want you to remember that water flows from the smallest numerical negative towards the larger numerical negative. So this actually is incorrect here. I thought I corrected this. So this should be this is right. So we have 0.02 to 0.06. So which of these is actually the biggest number? Remember, on a negative number line, the 0.02 is a bigger number than 0.06 because this is a bigger negative. So it's actually a smaller number. And I just want to make sure that you have that pointed out, because sometimes when we're taking a look at these numbers, we automatically assume that the 0.02 is smaller. On that note, I'm going to head and take a pause. I want you to review water potential with Bozeman Science, Mr. Anderson. He's absolutely fabulous. I know I've introduced you to him already, and I hope you have a good time.